So, thank you all for coming. Before I go through with the slides, I just wanted to give some context of where this came from, why it was created, and so forth. Early this year, I started learning about machine learning. So I started with Andrew Ng's machine learning course on Coursera, which I guess most of you know, but there's some of you that don't know it, or you're starting in the area you're curious about it. I think it's a really good place to start. It's got some good foundations, very well explained. And afterwards, I did the deep learning course on Udacity. And after these two courses, I wanted to apply this knowledge to something more concrete. And I also wanted to do something in Python, in Tensorflow, and know what it would be like to train a model in the cloud, so using the GPU. And at the same time, I was very interested in reinforcement learning. It was very interesting for me if I can create a program, an agent, that can play a game by its own, just with access for the screens and controls, and maybe something more like the score. And it happened that Google, DeepMind, probably had done that, and they trained 49 Atari games, quite successful. And this is one of the results. This is Breakout, this is the agent playing Breakout. As you can see, it took the optimal approach. It just took, it placed the ball on the top and destroyed a lot of blocks in one go. And I wondered, well, can I take this algorithm and apply it to a different game, like Outrun? And this is a more visually complex game compared to the Atari games, so maybe it would be a bit harder to train. But the principles are the same, so in theory it should work. And afterwards, so I trained it, and this is one of the best results. This is on 8 times time lapse, so you can have an idea of how it behaves throughout the 5 stages. And one thing you can notice is that there's no traffic. So this is just to make it simpler and more deterministic, because I just want to have something working in less time. And also another choice I made was to train this agent without the time limit. So normally what you do, you just train this with time limits, like you would in a normal game. So this means that the agent would start, then the time would end maybe on the first stage, it would go back, it would start, it would go to the second stage, go back. So what I did was, the agent had no time limit. It could just go throughout the 5 stages and experiment a bit more. And I found out that this yielded some better results, and I think it's because it got a broader training set. So I think it got a better generalized learning because of this. And this is not perfect. This is not the perfect approach it's taking. Like it crashes 3 times throughout the run. And it's being run with the time off, because if you put the time on, it's like 80 seconds in easy mode. It actually doesn't get past the second stage. It's near the checkpoint, but it's not enough. But I think overall it's kind of decent, and it can stay on the road, doesn't crash too much. And there was a thing that I didn't try, but maybe it's interesting, and it would be to take this agent and train it on a different track, like a completely different track, like a mirrored track, for example. And I think the emulator lets you do this, but I didn't want to try it. Yeah, it's just a small note about it. So what's powering these two things? This deep learning. And you can think about it in 3 major blocks. It's Q learning, it's deep neural networks, and some other concepts just to aid the algorithm. And we'll start with Q learning, which is a reinforcement learning method, which is quite popular, and it's really good for problems like this, where the agent all he knows or rewarding is the action after actually doing it. So the agent does an action and says, oh, this was quite rewarding. It does another action, this was very bad. It doesn't know the whole model. It doesn't have the whole knowledge about the world. So learning is quite good for that. And I think that the good way to explain this is through an example. And this is a canonical example in reinforcement learning, which is a grid world. And each of these squares here is a state. And this is the agent. And this is the obstacle. So the agent, for example, if it's here, it cannot go up, just stays in the same place. This is where we want our agent to end up. This is our goal, it's a terminal state. And we'll reward the agent with a reward of +1. So we just want our agent to fall here. And then the episode ends. And this is where we don't want our agent to fall. It gives the agent a reward of -1. And just one more, there's a penalty when the agent, well, not when it moves, but when the time passes, when it wants to move. So this is just to, it's like an incentive to make it move faster to the goal. But we can see the whole grid, and we can see, oh, the agent can just go through here or through here. But the thing is, the agent is short-sighted, so it cannot know that. It cannot know that this is the optimal path, for example. And to aid us, to aid the agent with that, we have these Q values. And we can think of these Q values as the quality of an action. How good is the action to take the agent to the goal? So the higher the Q value, the more quality that action has to take the agent to the goal. And well, they're all zeros, so they're not very useful. But we can train it with this Q value iteration, and we'll go through about it. And just to explain what's happening here, we have this alpha, this gamma. The alpha is the learning rate. So this will weight how much the Q value will change per iteration. So it just weights the current value with this error here. This is our error. The gamma is the discount factor, which sits here. And this is going to weight the immediate reward versus the long-term reward. Because this is the immediate reward, this part here. This is the long-term reward, which is the maximum Q of the next state. Next we'll have, so this is time t, so it's the current time step, and let's say we go right. So a note about this is that this is deterministic. So when we say that for the agent to go right, it actually goes right. So it will do this. It will go to t+1, which is in this state here. If this would not be deterministic, if the transition model would be stochastic, then it would mean that we tell it to go right, but that there's a probability that the agent can go up, or it can stay in the same place, or it can go to another place. You can think about it as if the agent was a robot. So you tell the robot, go right, but then the wheel skips and doesn't go anywhere. So there's that probability if it's not deterministic. But this is deterministic, so there's not that problem, it just goes here. And why do we want to go here? Bear in mind that this is just the training phase. We want to go through all the states and find out which are the best Q values, the optimal Q values. So the approach we are going to take is to always go to the action that offers us the highest Q value. There are better approaches to do this, but for the sake of this example, I think it's the best one. So According to that approach, we have for the Q value for up, down, left, right. They're all the same, so we can just do a random action. We'll choose the right one. So since we're telling the agent to go right, this is the current Q value, because it's the Q for state on time t, so this one, and for the action to go right, so this one. And it's 0. So we have this part here and this part here. This is the immediate reward, as we've seen before. It's a penalty per time step. So we've got the immediate reward and the maximum Q of t plus 1. So t plus 1 is here. This is the state on t plus 1. We just want the Q that's the maximum value. They're all the same, so the maximum is 0. So now we have everything we need. We have the current Q value, so here it's 0. We have the learning rate, it's 0.5. We have the reward, which is negative 0.04. Then the gamma is 1, so it's easy on the calculation, so we just take this maximum Q, it's 0, so it just zeroes out. Then we have the current Q value again, so 0. And we end up with negative 0.02. And we're going to update this Q value with this new one. And this is what we want. We want to go through all the grids and just update these values as we go on. Yeah, so it's the same situation here. We have all of them are the same, so according to our approach, let's just choose a random action. Let's go right. Same. We can choose right, we can choose up. Now we're on the terminal state, which means that there's no state after this. The current Q value is 0. The immediate reward is -1, because we said that this is the one that we don't want our agent to be in. So it rewards -1. And the maximum Q for the next state is 0, because we don't have a next state. And you'll see that this, compared to this, it's quite low. It will be 0.5, -0.5. And the colors all changed, because the colors are relative to the values. So now we restart our episode, and we're going, according to our approach, we're going to just choose a maximum Q here. We can choose up. So we have those 3 options. We'll just choose up. We can go up again, right, right, right. Then it's the same situation as we had before, but it's the positive reward. So we just get 0.5 here. This is a calculation, but the sign is changed. Right now, so according to our approach, we have these 2 options here, either left or right. So let's go left. And you'll see that the maximum Q is 0. And why is that? Because the next state will be this one. We'll just follow the same state. So the maximum Q is just 0. So we'll update, we'll go down. Then all of these are the same. We can go to the right. Now we can go down, up. Now you'll see that we're going to go left, and the maximum Q is -0.02. So from all of these, it's the maximum one. Now we can go up. And I'll skip through a bit. Now it's quite interesting what will happen now. The maximum Q for the next state is -0.5. So this will affect this calculation into making the new Q value much lower. So what will happen is that we're going to start to propagate this negative value throughout the adjacent states. And that's what we want to do. We want to propagate this negative reward or positive reward in order to create some virtual breadcrumbs for the agent. So this will get lower and lower, and it gets to -1. And we'll restart and just skip a bit. This is the same situation, or almost similar. Just the Q value here changes. It's -0.02 because we already visited this state. But the same thing will happen. The positive value will just propagate to the adjacent state. And now we're with the agent here, and we want to move right. And the maximum Q value is 0.22 here. And same thing, it's going to affect our calculation into having a higher Q value. So the propagation is not only for this state, but for the other ones. It's just going to propagate throughout the grid. And same thing, just propagating the positive values. And it found as well that there's another way here. And if we just go on, it just reinforces that path. And eventually we'll just end up with something like this. This is not the optimal Q values, but it's very proximate to that. And what's the advantage of this? Now that we have our Q function trained, because if you look at this, these values are just discrete values from a function, which is this one. So now we can just take an agent, we can place it, well, anywhere in the grid and tell it, well, just find the goal. And for example, imagine that the agent will be placed here. You have to remember that the agent is short-sighted. So it only needs to know the Q values in the current state. So it will just follow the highest Q value. So if it does that, follows to here, it just goes up, right, and just gets to the goal. We can put the agent here, for example, and if we know that minus 0.09 is the maximum Q value, then it goes right, then it goes up because it's the maximum, up, right. So we now have some virtual breadcrumbs for our agent to follow. And now there's 9 actionable states. What I mean is that the states that have the 4 triangles. There's 4 possible actions, there's a left, right, which means that just in this state, these ones that have triangles, there's 36 Q values. And we have to store them somewhere. We can store them in the table, for example. But in our case, we want to train for a video game. We just want to use these pictures. So this means that this image will be the representation of our state, which is much more complex. For example, here you can represent this as a XY coordinate, or I don't know, a number. And all of this is the representation of the state. And let's say we water this down and we resize this to an 80 by 80 image, grayscale image, which means that we have 6,400 pixels, and let's say that each pixel can have 256 different tones. So this means we have 256 power 6,400 possible states. That's a lot of states. Because if you just go forward with it, the image will change to a completely different state according to this representation. And more we have, for example, 9 possible actions. Because in a game like this, you can accelerate, you can brake, you can go left, you can go right, you can do a combination of those. So 9 possible actions, it's decent for a game like this, which means that if we take this approach, we would need to store about, well, this much data. That's a lot. So this is quite unwieldy if you want to store this in memory. And that's not the only problem. The generalization problem is quite bad, because imagine this is a state, and you trained this for some states, and now you receive a state just like this, but one of the pixels is just like a bit darker, just one bit darker. But you look at it, it's the same. But for this algorithm, it's completely different, so it doesn't know anything about it. And it says, well, I don't know about this state. We have to start from 0. So So you lose a lot of information, and also not just that, but if you train for a portion of these states and then you're evaluating like we were doing before, and you feed it a state that it never saw before, it will just throw the hands in the air and say, well, I don't know how to do with this. So that's two big problems with this approach. It's the generalization and the memory problem. And this is what I was talking about. We were just updating key values on the table, for example. This function is just a set of discrete values. But what about if we approximate this function? So this just turns out to be a regression problem now. And we can solve this with linear regression, for example. And in this case, what represents the function is just this set of weights combined with features. So for example, let's take the image example. Let's say that our feature 1 is the value of pixel in the left uppermost pixel. Then F2 is the representation of the value of pixel next to it, and so on and so forth. And we somehow represent the actions as well. But maybe we would end up with 6,400 weights, a bit more, maybe twice, maybe thrice. But it would be much less than 256 power 6,400. So this is much better. We just have to record, we just have to keep track of these weights. So memory-wise, it's much better. And to do the generalization, it gets better as well, because imagine that we train this for a bit, the Q value, the Q approximation is getting quite good, and then we receive a state that you never saw before. You can, with your approximation, you can take advantage of the data you had before and make an educated guess of what the Q value could be. And the question is, how do we train this approximation? How do we change this weight? Well, if this is a linear regression, we can just do, for example, the least squares approach, and we'll just end up with something like this, where we take the weights according to this error and the feature that we calculate. And what is this? What is this error? Well, it's the target value that we strive for. It's the difference of that. It's the target minus the prediction. So what's the target? What's the prediction? We already know that, actually, and it's here. The target, it's the reward plus the maximum Q value. That's what we aim for. And our prediction is this Q value. So we just have to ask for our Q value to this approximation. And we take this, we put it here. We know how to update our weights, and now the situation is much better. But there's still the problem with this approach, which is taking that image example again. An image, if you use the image as a state, the approximation you will do with the Q function most likely won't be simply linear. It won't be like polynomial 1. You'll have to do some nonlinear mapping to it. You'll have to use other features. You'll have to raise the polynomial degree. But that's really hard to handcraft this kind of features. That's image processing almost. So we don't really want to do that. But there's something that can help us with this, which is deep neural networks. And the thing with deep neural networks is that they automatically learn a set of features, so we don't have to worry about it. It gets much better. So we have that automatic feature learning, we have generalization, and the memory problem is much better because we just have to store the weights as well. How do we use this? Then we just do this. We put the state, we put the action to the network, to the approximator, and it gives us a Q value. And to train this, same thing as before. We have our target, we have our prediction, then we can just square it. Then we have our log. We can do backpropagation on it. And to find these values, for example, this prediction, we just have to feed forward the network. So when you put the state, when you put the action, it gives us the Q value. The reward, we will know with our reward function. The maximum Q value is where it may be problematic for this architecture. And that's because we want the maximum Q value for the next state. So let's put the next state here, but we have to find out what's the maximum one. So imagine you have 9 possible actions. You'd have to put the next state here, you'd have to put the action 1 here, then you'd have Q value for action 1. Then you do the next state, action 2, Q value for action 2. So on and so forth, and then until you get the 9 Q values. Then you pick the maximum one, and that's your maximum Q value. That means that for 9 actions, you have to do 10 forward passes just to get your error. So there's a better approach to this. That's what DeepMind did. They shift things a bit around and said, what about if we put the state as the input, we feed it to the network, and the network just fans out all of the Q values. So this solves our problem because now if we want the max Q value, we put the next step, the consequent step here, we feed forward, and we just calculate the maximum out of these. So just feed forward for the maximum Q value. And also, if we want the prediction for this state and this action, we just input this state and choose the action that we want. So 2 feed forwards versus 10. So it's much better. And how do we implement this? How do we implement the whole algorithm? I could show you the pseudocode, the lines of the text representation of that, but maybe it's more approachable if it's more visually through images. So I'm going to show you how I implemented this in the project I mentioned. And this is what we aim for. This is the end game for all of that. And we have our emulator here. It's Cannonball. It's our electronic emulator. And we're going to have this. First of all, we'll have the initial state here. And you might wonder why are there 4 frames here? We want 4 frames, 4 consecutive frames, because we're going to stack them and then feed into the network. We want our network to have a sense of movement. Especially for these games, it might be quite important to have that sense of movement. So we're just asking for the emulator, give me 4 consecutive frames. And then we pre-process it, we resize them to an 80x80 image, we take out all of the colors, and then we stack all of the grayscale images like we would in a colored image, so like various layers. And then we just feed it to the network. And like we did before in the grid world, we'll just pick the highest Q value, and that will be our best action to get to the goal. That's what we want. So we pick the highest Q value and the action associated with that, and we repeat that action 4 times. And 4 times why? Because we want 4 frames. So for example, we choose the acceleration action. You do once, you get 1 frame. You do it twice. You have 2. Then you get the 4 frames that you want. But the network, we're supposing that the network is already trained, but it's not. Just a bunch of random values. So we need to train this network in order for all of this to work. And this is what we'll see now. This is not training yet, but what we're going to do here, we're going to collect replay memories. And from those replay memories, we're going to train the network eventually. So our objective here, I can show you now, we want to fill out these replay memories And this is a queue of memories, and it's a fixed size queue. It means that if we imagine that the queue is full, we put a new memory there, then the queue is full, it's going to discard the old replay memory. And why do we do this in the first place? Why don't we just fit it in the network? We want to have this separation because it makes the training more stable, breaks some correlations with other targets. So it just makes everything more stable. But in the beginning, we won't have any replay memories. So let's start out by doing this pre-training phase where we just do some random actions. We just go around and do random actions to explore the environment. And we want to fill out this replay memory, which describes how we acted, how good was the action. So let's take this pre-training example. We have our initial state, as always, and we'll just do a random action, so we'll generate a random action. We know which action it is, so we have this information as well. Then we'll feed that random action to Cannonball, to the emulator, and step through. And it will give us what is the next state, what are the next 4 game squares. So we have the consequence state as well. And also, after we do that, it gives us the speed and if the car is off-road or in the collision state. Why do we need that? Because we need to calculate some kind of reward. We need to know how rewarding was this action. And we're going to calculate this through these 2 things. And after we calculate how good was this, how good is the reward, we put it here. And now we have our replay memory that we need, and we put it in our replay memories. So this is the pre-training phase. After we finish the pre-training phase and we have some memories that we can rely on, we start the training phase. This is where we actually start training the network, which will be happening further down. But at the same time that we are training the network, we'll be doing this epsilon greedy approach, where we'll start out by, so the epsilon regulates between exploration and exploitation. Exploration meaning it just does a random action. Exploitation, it picks the action that it thinks is the better one. So it picks an action from here, from our network. And how is this regulated? We have this epsilon, which tells what's the probability of picking an exploration action versus an exploitation action. So we can start with the epsilon at 1 in the beginning of training, and then so we'll do always random actions. But as the training progresses, epsilon will go down, just to go down, and the probability of picking and exploiting action will be higher and higher and higher, until we get to the end of the training well, where the probability of picking and exploiting action will be much higher. And it makes sense because in the beginning we don't know anything. The network doesn't know how to get around. So only by the end it makes sense to actually exploit what we learned. So if we actually exploit, the probability is favorable for that. Well, if we pick that, then we'll just feed in the initial state through our network. Like before, we pick the maximum key value, and we have our action. And we put the action here, and we have everything that we need to create the replay memory. So this was creating the replay memories. What do we do now? This replay memories, you can think about it as your training sessions. And we'll just pick, we'll just get a mini batch out of this. And in this example, in the project as well, it's picking 32 random memories. So we just sample some memories from replay memories. And what happens with this? So one more thing, we have 2 networks here, And this is the network we were seeing before. This is the one that actually is going to be playing the game. But this is the one we're going to train. And having this separation also creates more stability in the algorithm. That's why there's two networks here. So what do we want to do with this? We just want to find our error. How do we find our error? Just like before, we want to find our target and our prediction. To find our prediction, we just have to go here and take these two parameters of the replay memory. And we'll feed in the initial state to the network that's being trained. And we're going to pick the action that we did. So for example, in the replay memory, we did the acceleration action. We're going to feed this in, and then we're going to choose the acceleration key value. And this will be our prediction for this key value. Now we want to, at the same time, we want to compute our target key value. So as we've seen before, the target key value is the reward plus the maximum Q of the next state. We have the reward already because we already calculated this before. So there's the reward, it goes here. Now we need the maximum Q value for the next state. We have the next state as well, so we just feed it in. It's the consequence state. We feed it to our network that we use for playing, and then we get the maximum Q value. And now we have our maximum key value for the next state. With these two, we make the difference. We can do the square of the difference. We have the loss. We do back propagation. So we just train this network, and every fixed time steps, for example, 10,000 time steps, we clone this network to here. So eventually they'll be up to date. And this one will be discarded in the end. This is the only one who will want to play our game. And this is the whole thing. This is the whole algorithm. About deployment. To train this agent, I trained this agent on Amazon Web Services. And I chose to do it with spot instances. So the difference is you have on-demand instances and spot instances. The on-demand ones are the normal ones you get. You go to Amazon, you say, I want an instance, and it's for you. You just have it for a period of time until you terminate it. The thing is, you pay for that reservation. You pay a lot more. So what you can do is resort to the spot instances, where you can bid how much you want to give for that instance, hourly price. So for example, we have some GPU instances. I used the G2S large. It was the only one that was available with the GPU at the time. And imagine this, imagine that the bidding is 10 cents. Amazon says you have to bid at least 10 cents to get the spot instance. And I say I want to give 12 cents per hour. So the instance is mine for now, but then the bid can go up. And if it goes up, I lose the instance if I don't bid as much or more than what they propose or what they dictate. So what happens is that you can lose your instance mid-training, and the training can take a lot of hours. So I had to make something to take care of this. And the approach I took was to have an external EPS volume, so it's an external drive. And I would have everything that would persist, that would outlive the instances here. So the training results would all reside here, the source code for the agent, the source code for the emulator, the Docker files, the Docker images. And what this creates is that, imagine that if this instance just goes down. I can instantiate a new instance. I still have my training results. I can just put a new container there. It's faster than actually installing all the dependencies on the instance. And that's pretty much it. The source code, I would get it directly from GitHub. And if I wanted to get the training results, mid-training or after training, I could just pull it down. I had like a set of scripts to do this, so I could do everything on the command line. And that was it. That was the architecture or the approach I took for that. So one final note, I just want to mention OpenAI's GIM and Universe. Because if you're interested in reinforcement learning, I think these are very two interesting projects. GIM, it gives you an environment for you to put your reinforcement learning agent. It gives you an assortment of games, like Atari games, for example, and problems. And you can then compare how good is your agent with other people. So it's really nice. It's a really nice project, which was created this year. And more recently, there's Universe, which was put live, I think, this Sunday. And it takes the Genes API and it's applicated to real-time environments. So they're even thinking about putting GTA 5 there, so you can train your agent to play GTA 5. But it's focused on real-time environments, so it's a bit different from this because we could just step through as we wanted. So it's a bit different. But they have starter agents, which leans on an algorithm that was published this year as well, which is like a step up from this algorithm, this DQ algorithm. And the basic idea, as I've seen, is that you have, instead of just one actor, one agent learning, you have several agents learning at the same time in different environments. And then the algorithm they used on that agent is kind of similar to the one we used here. So I think those are pretty much, these two projects are very interesting. So definitely, I think if you're interested, I think they're worth checking out. And that was the presentation. If you're interested, the source code about the project I did and the article in which this is based on is on my GitHub. And that is it. I don't know if you have any questions.
So how many hours did it actually take to train the video that you showed at the beginning, and how much did you spend?
I don't remember actually, but it was more than 1 day. The total that I spent, I think it was about 20 or 40 euros total. Because these spot instances, they're quite expensive. So the spot instances, no, the GPU instances, and I had to try it a lot of times. So yeah, it was a bit costly. But if you do it right on the first time, well,
It's not very costly.
But of course, like if you get the tower, if you build a system on your own, it's so much better because I didn't have to buy my own computer, my very good GPU and so forth. So in that case, yeah, it's cheaper.
And were you able to run the emulator at normal speed or sped up, or did you have to like slow down, or did you have to slow things down because it would take too long to update the networks?
I had to modify the source code of Cannonball because it was actually fixed on the FPS.
Yeah.
So I just made a flag there so I could just step as fast as I could because that was a big bottleneck. I was just
You sped it up a lot.
Well, more than 30 or 60 frames per second. So, but still, it was an inconvenience. I would see that the major weight, one of the major weights, would be on the emulator because I was just waiting for it. But I didn't want to optimize it even more. It's a big chunk of source code. But yeah, it wasn't too optimized for this case. And I took the sound out, I took everything I could. So, but it wasn't, I think it wasn't enough. I think it could be better. When compared, for example, with an Atari emulator. I think you can get much better performance out of it.
If you would run the more than one day, imagine for 2 days or more, would you be able to have the perfect score?
First of all, I don't think so, because the reward function that I used, it was a bit more greedy. So what I mean by this is that, for example, if the car would go off-road, I would tell it, this is bad, don't do it. But I found out that the optimal approach to play this game is to actually accelerate. So accelerate, stop, and then put the car in between the road and off-road. And you just go into never stop. But to do that, in order for the agent to learn this, I couldn't just tell it, well, you cannot go off-road, because it actually has to go off-road. But what that means as well is that it had to explore more, it would spend a lot of time off-road. And I wanted to cut down on the learning time, because the learning time is huge. So I wanted to cut down, so I tried to just make a more direct reward function. That's why I used the collision state as well. I used the off-road as well. Because otherwise I could just use the speed, for example. I could just tell it, just go as fast as you can. That's your reward. And eventually it would find it out. But yeah, I took that approach in order to be faster to MVP.
Okay. Speaking of the reward function, I still didn't have the time to read this paper where you talk about the reward as a function of speed. But what do you think would happen if you try to... So it doesn't seem that this reward is very much aligned with the least time possible on a given distance. So what if you try to train it on a fixed distance and just give it a negative reward for every second, right?
Oh, I see. So it's
do you think that would work?
Reward.
Yeah, something like that.
Don't give the reward.
Exactly.
Maybe it would work out better, but I'm not sure. To be honest, because.
And how much would that change the whole approach? Because it would have to be so much
approach.
more.
You just have to change the reward function. Is that what you're? You just have to change the reward function. The rest is exactly the same.
Okay.
So, but what I did was, if the car is stopped, then you have a penalty. But if you start moving, then you have a small reward. It just progresses, and I made it like I think it's a square root. So I don't know what it says. Logarithmic. It's logarithmic, yes, but it starts with 0, so yeah, it's logarithmic. So it just, instead of being linear and if the speed is very low, the reward would be very low as well. So I tried to give it a high reward just as long as it was moving. So that was my approach to it. So it's definitely not the optimal one. I won't give you the optimal results, but I've seen that in last time it gave me better results.
Okay. And by the way, do you have an idea? Let's say you have 10 times or 1,000 times more time or power to train this. Do you know what would you change if you had like 1,000 more hours or CPU, GPU?
The reward function for once, and I don't know. I think maybe I would keep the network as it is, because I don't want to overfit as well, put too much things in it. But I had some problems with divergence as well, so the loss would go up. But the thing is, I saw that the average Q value was going up as well, and there was a point that I knew that it would just stall. But I didn't get to that point. What I think it would happen, I'm not sure, is that if I arrive to that Q value, that average Q value that I described, that the loss maybe would stall as well, but I'm not sure about that. It just takes a lot of time just to do that. So maybe I'll just change the reward function and do it as it is, because that's what Google did. They just have a very simple reward function, and they put a lot of processing power on it. So I think that's why I would do it.
And by the way, they do have much more computing power, right? Do you have a sense of scale? If DeepMind was to publish this on how to run this game, how much more they would train it?
I'm definitely not sure the quantitative thing, but it's definitely more power. They wouldn't spend 2 days just doing training. They do put more GPUs, because you can just put a lot of GPUs on this Tensorflow. Although they didn't use Tensorflow, they used, I think it was TI. But you can just throw everything on it. They have big data centers, so I guess they could just allocate a big portion of it, but I don't know how much.
Is the high-level architecture parallelizable much more? So you have like training networks being updated and then replacing the playing networks at certain intervals and whatnot. Is that could you be doing that in parallel, and then those updates coming in like more often or something?
You mean this algorithm?
Yeah.
Well, I think the only parallel thing you could do is the approach I talked about in the universe. It's actually having many agents doing different things at the same time. I don't know if that answers your question, but I think you can only do this. Can only do all of this in one go. It has to be synchronous because you actually need to step the game. So your environment dictates how much you can go forward. So I think the only parallelizable thing you could do here is to actually have more agents playing the same game.
How would you transfer learning from one agent to the other?
I didn't read the whole thing, but what I've understood is that they have one single network that's shared between all the agents. So I guess they have maybe some logs, or not logs, but maybe a semaphore.
No, the knowledge is in the network, so
yes,
if you share the network.
Yes, if you share a resource, then you just have
You don't even need to use locks or semaphores or stuff like that. Some distributed learning methods can do concurrent updates without locks. So meaning that the order can change the outcome, and if things are sparse enough, it still works. There's something called hog wild, very different from deep learning, but that's one of the papers I know about this.
Yeah, but you have an error, so the error, you can always update the weights no matter what.
You can use something like a stochastic gradient update, and you just add the number of stochastic gradient updates for multiple agents in the same method. That should also work.
What you mentioned, log wild, that's actually what they used in this algorithm.
Really?
That I mentioned. So this is actually.
Hog wild is like 2 years old, something like that. Maybe we can speak about that in a future session.
I was wondering if you had thought of any strategies as you use more computational power and as you achieve a maximum of the performance that you need to obtain, you might be arriving at the local maximum. So I was wondering if you were thinking about any approaches in terms of, for example, novelty search
So I think the way to do this in this kind of problems is to actually explore more, because if you're hitting a local maximum, maybe it's because you're just following through the actions that you think are best, but then you're missing a path that's unknown to you. So maybe a way to get around that local maximum is to actually explore more. So in theory, if you explore every possible state many times, it actually arrives to the optimum, to the highest the highest maximum you can. So I think that would be the approach to actually explore.
Did you consider if the computer play was actually a human could do it, like, or if it was your system was able to click left and right faster than a human could play it?
The response time of this system, it's just a bit up from the response time that the human has. So I think it was 40 milliseconds, I'm not sure.
It's probably the time with the 4 frames.
Yes. No, actually no, it's not 4 frames, it's more. I made a gap in between them so I could make the 40 milliseconds. But I think the average response time of a human is 20 or 10, if it's really good. But it was a bit more than a human. It wasn't lower down. But in this type of game, it doesn't really matter because, well, you have a lot of time to do the returns.
In the beginning, so you had 256 raised to the 6400 possible states. But then you did some calculation and you reduced only to 6400 possible states. Is that correct?
Hypothetically, yes. That's because we're just approximating the Q function. We're not storing every possible value that we have. It's the same thing that well, it's just approximating the function. You have a set of weights that take care of all those.
It's like you discard some info. Is that it?
No, I don't think so, because there's a lot of redundant information, so that gets encoded in the approximation somehow. So in theory, you can actually map all the information if you have a good enough model. And normally in this kind of cases, there's always some kind of repetition, so you can take advantage of it. So you're kind of compressing your information, so to speak. That's why neural networks are so good at compressing stuff. I think that we need something that could create a compressor, could create a neural network that could compress images, for example.
Yeah, it's an encoder.
An encoder, yes. So
It's called autoencoder.
Okay. Why 4 frames?
that's the same thing that we used
Okay.
in the queue.
And the 40 milliseconds.
The 40, I didn't want it to be too low because if the response time would be very low, then I would just take more time training.
Okay.
So it would be faster. It is a good trade-off.
I was just wondering, in this implementation you're using the 80 by 80 image to process. I was wondering if it was possible to have any approach, for example, where you could, I have no idea, but for example, to introduce the notion that there's that instead of analyzing the whole picture, analyzing just the road and the car and maybe the obstacle, they were introduced so that you can simplify because if it's, say it's a human looking at this picture, you're not processing every single pixel, you're focusing on
Yeah, but neural networks do that.
Yeah. That's why they're pretty nice for this. They automatically learn this kind of feature for you. So you don't have to create filters and all of that. So it's pretty nice.
Cool, thanks.